Hello, how are you? Arunava here. Today we're going to talk about linear regression. Linear regression is a class of machine learning algorithms that is called supervised machine learning algorithms. Supervised machine learning algorithms are the ones where the model utilizes all the data points and their outputs to uh, predict the unseen data, right? And there's three classes of machine learning models: supervised, unsupervised, and semi-supervised, right? So in supervised is what I just told you. Unsupervised is the one where model sees just the input variables and doesn't see the output to train the model. Semi-supervised is the one where the model trains itself, seeing a few of the output data points, a few, and a rest of it doesn't look at, right? So again, to come back to linear regression. Linear regression is an example of a supervised machine learning model. And in a supervised machine learning model, it sees the data points and its outputs to train the model itself. So we need both the input variables and the output variables to use a linear regression model. All right. So let's take an example of of linear regression, and let's take an example of in case of linear regression helps you predict continuous values. Okay. Continuous values. What do I mean by continuous values? Continuous values are like prices, age, weight, height, and so on and so forth. Uncontinuous or classes are examples where you're predicting, let's say, the species of a dog, the brand of a shoe. These are classes, right? So yeah, okay. With that, let's talk a bit about linear regression again. So linear regression is one of the simplest regression models. It fits a straight line through the data. So we're going to talk about three things. First is, what is linear regression? And I think I have given you a bit of an idea about what is a linear regression. It's a supervised machine learning model that sees the output as well as the input to train the model itself. And then it predicts continuous values like prices, ages, weight, and height, and so on and so forth. We're going to look at the function or the hypothesis function of the model that is used to predict the values. And we're going to look at a couple of examples along the way, like I'm talking about. Like prices, age, weight, height, and so on and so forth. All right. So in case of linear regression, we have in the simplest case of linear regression, we have two variables. So let's draw a graph quickly. So this is x and this is y. So let's say there are two variables, and let's take an example. Let's say prices, right? So let's say this is 23, 24. These are the years: 25, 26. 27. So these are my x's, and my prices are 150, 200, 250, 300, 350. Okay. So, and given this, so this is a very simple data set where so let me just quickly put some values here. So let's say these are my data points where all my prices are increasing, decreasing, and this is all over the place, right? So as you can see, there's a linear relation to this to the x and y. So if I decide to draw a straight line through here, then then this particular straight line will give me a very accurate estimate, right? A very accurate estimate of my unseen data, right? It'll give me a very accurate estimate of my unseen data. So that is an example. So we have this, so this is a house pricing example. right? So we're given the year or given something in between. We are predicting the house price, the prices of house in an average in that particular year, right? So with that, we can talk a bit about what is x and what is y here. So x is the independent x. We call x as the independent variable. So it doesn't depend on this on anything else. Y is the dependent variable. Because y, the value of y, that is the price of the house, right? The price of the house depends on the year, right? Depends on the year. So now let's come to the hypothesis function, that is a linear regression model that is used to predict unseen data. So it's nothing complicated. It's y is equals to mx plus c. Y is equals to mx plus c is the function of a straight line, and that is exactly what linear regression is, a straight line in the two-dimensional world. And that's why, and very simple thing, linear regression model is y is equals to mx plus c. So let's break down things a bit. So x over here, the x over here is the dependent variable, sorry, the independent variable, right? Independent variable. Y depends on x, right? Y equals to mx plus c. So y depends on x. So that's why this is the dependent variable. And we have the c and the m. So c is the intercept. We call c the intercept and m the coefficient. Nothing fancy, nothing fancy. Let's take a few examples and let's just clarify through what is the intercept and what is a coefficient. Okay. So let's say I have this graph over here and my model looks something like this, right? So this is 0, this is 1, 2, 3, and so on and so forth. This is 5. Let's say this is 5, this is 6, this is 7. So as you can see, when my x is 0, right? When my x is 0, right? The value of y is 5. So when x equals to 0, y equals to 5. That is my intercept. Okay. So what is an intercept? Intercept is the value of value of y when x equals to 0. Okay. So that. Okay. And what is my coefficient? Right. So let's take another example here quickly. So let's say I have this graph. And let's say this time my intercept is 0. Right. And this is a linear graph where this is 1, this is 2, this is 3, this is 4. Okay. And let's say for the corresponding ones, this is 10, this is 20, this is 30, this is 40. So as you can see, like with each passing value, with each increasing unit, so if the unit increases by 1, if x increases by 1, my y increases by 10 units. Okay, so that is the coefficient. So let's try to formula define it a bit. So let's say I have, so let's say if I increase x by 1 unit, so let's say the displacement of y, the increment in y, increment or decrement in y, if I increase x by 1 unit, right? So if I increase x by 1 unit, it is increasing by 10. So my m is going to be 10, right? So let me just put this in formula. So x is equals to 10x plus 0 because my intercept is 0, right? So when my x is 1, my y is going to be 10. When my x is 2, y is going to be 20, 3, 30. Exactly how we saw in the graph, right? Now let's take another quick example just to combine the concepts of intercept and coefficient. So let's say this is my graph. Let's just keep this simple, right? So this is my 0, this is my 5, this is 1, and this is 15, this is 2, and this is 25, this is 3, and this is 35. Excuse the unscaled diagrams, right? So for this, I think it's pretty obvious what's going to happen. is that our formula and our hypothesis is going to look something like this: 10x plus 5, where given x is equals to 1, y equals to 15, 2, 25, 3, 35, and so on and so forth, right? So that's a quick example, and I think you have a pretty clear understanding of of what is y equals to mx plus c, right? So given that, let's take a quick example. And let's just try to take a quick example here, right? So let's say we have this graph, right? And let's say I want to increase the intercept. So if I increase the intercept, then my model would look something like this, right? And if I keep increasing the intercept, the model will keep looking like this, right? And let's say I decide to increase. So let me just draw another graph here, just to take a quick example, right? So these are my data points. I'm not going to draw anything formally here, right? Let me just change the color quickly. And let's say this is my let's not draw this right now. This is my y, this is my x, okay? And let's say I have this straight line, okay? So let's say this is my model right now. This is my function right now. So this is my straight line. So obviously, as you can see that let's say I have to so given x, so this is my house pricing data, and let's say I have something like 26 over here, and this is the point I'm trying to classify, okay? So given this particular point, which lies somewhere down here, and given this value of x, so let's say this is, I don't know, 25.7, okay? And given this, I want to understand that what is going to be a possible value for this point. This is an unseen data. All these other ones are the seen data, right? All these are the seen data. This is my unseen data. The one in the brown is my unseen data, right? And this is the current condition of my model. This is the current condition of my model, which is lying over here. So based on this model, if I try to predict what is the value of y given this x, right? So given this x, the value of y. So given this model, first of all, what's going to happen is that we need to go up and up and up and up, and somewhere down the line over here it's going to meet, and that is the possible value for the y. I hope you followed that. So because the model is extending farther up and up, and my x is 25.7, I go farther up and up, and over here it collides. So the value of y is going to reside somewhere around here. I'm not drawing it because it's going to make a mess, right? And that is obviously not true because my data lies over here, and so this is obviously a very bad model. So what can we do, right? So we can increase the intercept. Let's try increasing the intercept. So what's going to happen if I increase the intercept is the model is going to go like this, right? It keeps going up and up because I'm increasing the intercept. So that is obviously not going to help. What else can we do? So the model is very steep, right? So if you see a model which is y equals to mx plus c, and if m is equals to 1 and c is equals to 0, it's going to be a straight line. It's going to be a 45-degree line. So 45-degree line, or when the intercept is 0 and the m is 0, let's skip the intercept. Let's just talk about them. Because if you increase the intercept, it's going to just go up. It's just going to go up over here, right? It's going to go up over here. Nothing else is going to happen. So the steepness of the line, let's just take this. The steepness is defined by m, or the coefficient, right? So if my coefficient is 1, my line is a straight 45-degree line, and 45 degrees is something that seems reasonable over here, okay? If I draw a 45-degree line, that seems reasonable, better than what I have over here, right? Okay, so if I increase m, then what's going to happen? The line is going to become more steeper and steeper and steeper and steeper and steeper. So obviously then in that case, what has happened is the current line that I have, right? The current line that I have over here is obviously a line that has a high m, right? So if we decrease the m, right? If I decrease the m, then obviously that line is going to fall down here and it's going to reach the 45-degree plane, and where it's going to be a good measure. So that is how we find a model that is we find a model that is a good fit for the data. So what we do is, given the line, given this initial line, we calculate the error, that is the distance between the line and the different points, and we take the average of this and we move the line such that the error becomes less, right? We move the model so that the error becomes less. I'm using the word line again and again because it makes it simpler to grasp. But we move the model such that this becomes simpler. The error becomes minimum, right? All right. So once we do that, we'll have a line something like this, and it is an almost a very good estimate for the data that we have. All right, I think that covers about linear regression. Okay, see you. Thank you.